Great. So please, the stage is yours.
Great, thank you very much. Well, good morning from New Zealand. Great to be with you today. Great to be joining this interesting conference. I did join the commencement before I departed for my evening last night, and it was great to see some of the early talks. So today I'll be talking about a project we've been running in New Zealand to look at the change in the plantation forest landscape through remote sensing and artificial intelligence. So I'll talk through some early results that we're finding and the nature of our design approach and how the artificial intelligence models were put together and really how they depict in some detail the nature of deforested land. Just a little bit of context first. So we're a fairly new company on the scene, just been around about a year and a half, established last year, based in Wellington, New Zealand. So we primarily provide consulting services and research around AI and machine learning. We actually are tagged to a US company called Lynker, who provide services for sort of federal government agencies and fisheries in hydrology, coastal systems, climate change, and so on. So we offer really a nexus, if you like, of compute, big data infrastructure with artificial intelligence and geospatial analytics. And we think the geospatial analytics piece is quite crucial really in terms of best practice land coverage surveillance, wetland mapping, land surface and micro land monitoring. So bringing those two capabilities together creates some really unique capabilities and results that are possible. So in terms of the project that I'm going to talk about now, we were commissioned late last year to undertake a full inventory of the extent of forest loss across New Zealand during the 2017 and 2018 calendar years. So every 2 years, our Ministry for the Environment, who are responsible for greenhouse gas reporting to the UN and other agencies, undertake a survey of forest loss in a 2-year period, but they wait for full 12 months post-harvest to do that analysis. And in the past, that's been a combination of field checking, fairly laborious, field work, or in some cases, satellite imagery was attempted, and in other cases, oblique photography, all of which are fairly labor intensive and quite involved. So what we proposed and what we have gone ahead with is a more automated approach, still using aerial photography, but applying a machine learning framework to that information. We worked with a couple of partners there, a specialist forestry observation firm, Carbon Forest Services, and a specialist fixed wing drone operator called UAV Mapping New Zealand, who we worked with to acquire the photography. So our design approach, fairly sort of a sequential workflow here. So firstly, there was an aerial survey which we undertook to scan a wide geography, and I'll show some numbers on that soon. We undertook some quality assurance of the photography, really to standardize the brightness, the contrast, the deal with shadows and terrain. There was a mosaicing process to turn each target, so each forest acquisition, into a useful product for machine learning. Then the crucial machine learning training and machine learning algorithm development piece, which I'll talk a lot about shortly and show you some of the results of those. So that was the phase where we turn those pixels into meaningful land cover determinations and a final recommendation in terms of the current land use. There was some post-processing and vectorization, which is really where we turn that data back into sub-area definitions, i.e. what's the nature of the land surface? Is it still deforested, cut over if you like? Is it maturing? Is it replanted, and so on? Has it been converted, in fact? And then finally, there was a multi-criteria analysis, which was looking at all those compositions of each forest area to determine a final land cover within the total harvest site. So just in terms of the photography plan, we did consider satellite imagery. We considered the high resolution, for example, Sentinel imagery, down to the more high resolution sensors like Planet, Digital Globe and the likes, Maxar. Really the nature of our geography in New Zealand, the cloudiness, the ability to get daytime coverage across such a wide sweep of land, 7,500 separate individual areas, some cases a hectare, in some cases 30 hectares. really prevented satellite imagery from being a viable option for us. So we chose to deploy fixed wing aircraft, capture 25 centimeter footage, direct vertical imagery. In total, we flew for 220 hours. That's a little example on the right-hand side here of the flight plan around Christchurch, one of our cities in the South Island of New Zealand. And you'll see the photo number in the red flight path is really the plan. That was 1 day's flying, approximately 200 forest targets. And we generally acquired 4 or more photos per target, which we use to produce our final image mosaic. Just to show some of the examples of the photography. So this is the raw imagery that we were working with. So you can see here some quite nice examples of newly plantation forest to the left, a fully harvested site yet to be replanted in the centre, and really a combination of some mature forest, a harvest site, and some native vegetation on the right-hand side. It wasn't always this easy. It wasn't always this nice. Those are relatively straightforward for an automated approach to classify. Many of the forested areas look more like this, and the upper two most examples, for example, show harvested lands, but with debris from the cut, and also perhaps there's been a period of fallow where the block is yet to be replanted. So the machine has to determine, are we looking at emerging vegetation or planted vegetation? And often that depends on the length of time and the growth rate of the vegetation. Bottom left as well is interesting. Due to COVID this year, we had intended to fly predominantly through the summer. We were forced to bring the aircraft back for, it was 7 or 8 weeks with the New Zealand lockdown back in sort of April, May. And we therefore recommenced flying in June, July. And so therefore some shadows became an issue for us. And you'll see there in the bottom left frame, there's a number of dark shadows which we had to deal with our models. Okay, onto the machine learning and the AI engineering. We at Lynker focus a lot on active learning. Now, active learning is quite a strong field of research in AI, which is really around human-in-the-loop computing. It relies on a technique called entropy sampling, which is used to advise a human trainer where a model may be struggling to distinguish classes. So to explain that a little further, this little diagram here shows an example. For example, if we take an unlabeled data set, take that raw photography that I showed earlier, we can build in stage 1 a weak model. We do some simple hand annotation, maybe a couple of hours to distinguish, that mature forest from the bare ground, from pasture, from plantation seedlings, emerging seedlings. A weak model then can start doing inference. That inference will produce proposed labels, which will be fairly random. It won't be particularly robust at that point, but the model will actually report an entropy score, which is a level of confusion or noise. And that entropy score will produce a guide to the human expert for further training. So if we move through the loop, a model produces some proposed labels, then allows entropy sampling to predict or surface up examples that need further training. And then the human expert can continue that training process, but in a very guided way. And we spin this process multiple times. Just a little bit more detail here in terms of that process. Really looking here more at a high entropy situation to the right-hand side of that sort of stack of bricks. A high entropy result would, for example, be in the bottom right-hand chart, where the model cannot distinguish particularly well between, say, those various forms of vegetation cover. And in some cases, those classes are quite similar. The left-hand side is an example where class A is nicely separated from the other classes. So that's quite an ordered situation, and that's what we're trying to achieve. So the model's essentially trying to move from right to left in terms of that bottom right chart using this approach. So with that engineering, what we do is we bring together the data into a presentation web-based interface. We surface this to some of our forestry partner experts who are very familiar with these terrains. And the machine itself was reporting those high entropy samples. In this case, you'll see I've just noted there this particular example, and I've got 2 views of the site here, which I'll talk to shortly. The model was predicting that to be grass pasture. Clearly that's not. So the human expert would re-annotate that example to a plantation seedling category. So this is the approach we use over time to train and improve our models. In the end, we've captured around about 15,000 training samples across our project to produce our results. And a little bit more here on the sort of example training records or classes. So I've got 6 examples here. We had about 12 to 15 total class categories across the project. And you'll note a two scale view here. And this was quite an important design decision we took for the model, which I'll talk about the architecture next. We asked the trainer and the model to understand context at a 70 by 70 meter resolution, sort of 5,000 square meters, and 10 by 10, 100 square meters. So that's the zoomed up view on the right-hand side and the more scaled out view on the left-hand side. You'll note with the plantation seedlings example, that's pretty clear really in both views. The second view, the harvest track's not quite so clear. Without that context of site, is that a area of bare ground of harvest, or is that actually a cutting site or a cutting track or a transport route? So we found a two-phase view, a scale view was very important to the model and the architecture. So the network architecture itself, we used a patch segmentation approach here, training on those 2 image chip pairs. So we used sort of various combinations. We used an Inception Vision 3 from Google convolutional neural network model. We looked at UNet and other models, and we really concluded that this 2 sort of dual approach model was really the smartest approach in order to classify in the end that 10 meter by 10 meter patch of ground. That allowed us really to really understand both scales quite nicely, and the Inception 3 network's a very good compromise, if you like, between efficiency and performance overall. So in terms of results, I've just got 4 or 5 examples here that explain the end game and the outcome from the approach. So left-hand side, I have here the original photo. The red boundary is the target area. So these target areas are known to be forest in plantation, and those sites are audited under the New Zealand Carbon Accounting System model. So we're essentially trying to diagnose, has the land use fundamentally changed? Has it been cleared and been replanted? Is it simply cleared and perhaps being prepared for replanting, or has it been converted to another land use? So the inference result you'll see in the center, this is the final result from our models, and we've got some categories there in the legend below. Largely, the model's done a pretty good job here. It's revealed that this is largely harvest site cutover. It's picked up some definition of tracks and built forests, which is the sort of harvest sites and so on. Some sections of pasture sort of outside the polygon, bottom right, top left, and some more mature forest. You'll see some more mature exotic forest, bottom left there. We run a final filtering process across the data, really to remove speckle and remove what we consider inconsequential areas, if you like. So the smaller little patches of, for example, seedling plantation the model has found. Visibly, it's determining that some of those smaller sites may be plantation. They may be indeed plantation, but in terms of overall scale, that's not material to this site. So the final classified polygon data set is to the right, and our end of our decision criteria is not replanted in this case. A more complex example here, we're seeing a site that has had replanting in the center and the top right. However, around the edges of this location, we're seeing still a lot of cutover, and it's not clear to the observer and therefore to the model that the site is fully replanted. So the conclusion here is a partial replanting, and these results go into an ongoing surveillance process. So every 4 years, if there's not a conclusive result in the subsequent survey, then there's a landowner discussion around that site and how it's managed under the greenhouse gas emissions program. An even more complicated site, and I wanted to show this one for a couple of reasons. We have some fairly mature native forest here in this example, and the models pick that up rather nicely. We have some plantation or some cutover and emerging vegetation appearing sort of in the right-hand side of the frame. We're also seeing some of that dark shadow through the winter photography here. And what we've done with that is these are these sort of no data pixels in the center and scattered throughout, is to hold those as no data and not record those, just because that can actually sway the model towards you know, an error position. So that was sort of how we handled that scenario. And the last one, which is a really quite a nice one, this is sort of the ideal outcome that most of the data we're working with we want to produce. And this is sort of the best practice where a site is fully replanted, it's appearing very clearly, and therefore it's a very clear and simple decision to assign that as fully replanted. So in conclusion, just some sort of key learnings from our project and what it means. We've found that deep learning is really very effective at learning patterns in this sort of complex type terrain. We've got a lot of heterogeneous land cover. The data is complex and noisy and a bit ambiguous in places. We find a dual multi-scale convolutional neural network model is quite a powerful technique, which sort of changes the problem from semantic segmentation to image classification at that 10 meter by 10 meter patch, which is sort of what we think the human brain is designed to do. So our training apparatus became far easier and faster to work with on that basis. Active learning is a very robust method to train and quickly train in a very targeted way. And overall, the models we've built here will hopefully have long-term future use. Providing the imagery is similar, the training libraries and the model's architecture itself will allow ongoing surveillance, really lifting a lot of the cost and the repeatability and the effort out of future modelling work for the Ministry for the Environment. So with that, I will pass back to the chair and happy to take questions.
So, thank you very much, Matt. That's quite something what you've shown. It's also very relevant if I think of the forest fires and wildfires in California at the moment, or it's actually globally the forest depreciation also if I think of Asia. So for the questions, I would hand over to Kerstin. I would remove the speech now and add the questions we have received so far.
Fantastic. Thank you again, Matt, for this presentation. I think it was really interesting, and I'm sure all of our delegates also very much appreciated it. So I will just start with the very first question, which is quite a long one. So Google Maps endgame is having all places mapped. Recent statements from Facebook point in the direction that they aim for mapping all buildings, including interior. Where do you see the end game for forest management? A global database, or what do you think is going to happen in our sector?
It's a good question. Certainly in the built environment, yeah, there is quite a focus on building, you know, large definitions of buildings, of roads, of infrastructure. But those are more permanent structures. I think in forest and natural landscapes, there's a change detection mentality that's probably going to prevail, which is using these sorts of techniques to produce point-in-time views of land cover, and the value probably is in the models and that long-term payback on can I then look at change across time through models. So not so much producing a long-term mapping data sets point in time, the ability to at any point in time detect change and look at current state.
Yeah. Makes sense. I know you pointed it out during the presentation, but could you maybe highlight once again why you didn't use satellite imagery?
Yeah, we thought long and hard about this, and obviously it would have probably saved a lot of cost in some respects. Really, certainly in New Zealand, and I think in any geography where there's such a wide coverage required, the kind of confluence of time of day, so it must be daytime, it must be really a good sun angle, it must be cloud-free or near cloud-free. And these are small sites. So often the satellite companies have a minimum tasking size, and they're sort of designed for large scale mapping, not very small scale distributed mapping. So it sort of brought the aircraft into frame. And we did look at the other end of the spectrum with drones as well, but the amount of data management required to to connect that data together and make that all work was even more laborious. So in the end, we felt relatively low flight fixed wing aircraft, not ortho rectified, so a single or 2 or 3 photos over a site was the fastest, most efficient approach.
Okay. Next question was, how many trees are needed to be classified as a forest? What did you use as a classification for a forest?
It's a very good question. We didn't do any sort of counting as such, although that is, we think, quite a achievable outcome, especially with this type of imagery. We were looking at the spectral response, really, of the vegetation. So we had experts in some ground truthing. We were looking at various species and the nature of native species versus exotic. So it was more the spectral texture and color and how that appeared in the imagery rather than the density or the number of trees.
Yeah, I feel like that's also a very specific thing to New Zealand, considering you have so many native trees versus the ones that have been brought in later into the country.
Definitely.
How much effort was needed for labeling the images? So how much of the project's time was invested in labeling? Did you use any special tools, or did you do that manually?
Yeah, good question. The little web browser interface that I showed with our active learning framework, we built that a JavaScript application really to connect those algorithms into a more easy, intuitive web application. So it wasn't a off-the-shelf tool, custom built for the project. We've developed that we think for other projects. An active learning web-based interface is quite a strong candidate for training models quickly. The other part of the question in terms of time, we spent probably around about 50 to 100 person hours training the model. We produced around about 20,000 annotations across 12 species or 12 land cover types.
Okay. Is your service used anywhere else other than in New Zealand?
No, right now we're using it only in New Zealand. We've done some work in fisheries and in sort of urban surface mapping in Australia and the US as well, but in forestry only in New Zealand.
Okay. Leading into the next question, what's your next goals? Are you looking for new partners, clients, maybe working with other governments other than the New Zealand one?
Yeah, great question. Yeah, no, absolutely. I'd love to talk to folks who've got an interest in this field and potentially see some value in similar types of projects. We believe that a continuous learning system is really the end game here, where we're looking at an active learning framework, good neural network design, specialists like forestry experts who we partner with in this project. We've partnered with ecologists here in New Zealand for some wetland work, which is another difficult category because they're quite heterogeneous surfaces. Fisheries is another one where a lot of fish species look very similar, and it requires that neural network design to separate species that are quite closely aligned. So in a lot of environmental natural habitat type monitoring and inventory type projects, we think this is there's a lot of scalability here, and love to talk to folks if they've got similar passion and interest in that field.
So you've all heard it, get in touch with Matt and you can all exchange the information you have. Thank you again for joining us so early, Matt.
Thank you.
And I will give it back to Vienna.
Yeah. Thanks a lot, Kerstin. Matt, if you are looking for cooperations partners or something, please do not hesitate. Either use the P2Match platform to set up one-on-one meetings, or additionally send us a call to action that we will just post on the LinkedIn channel of the conference.
Wonderful. I'll do both. I'll be available on that meeting channel, and happy to share some further information and talk to folks in Europe who might be looking at the same sort of field and beyond, to be honest, anywhere. We are a global world now, aren't we, as we can show with this type of conference.
Yeah, and I could imagine that this topic is getting really hot. This is also, it's one of the reasons why we made the first, let's say, special topic applied AI conference for forestry and the timber industry, because interest is spiking in the last months. And I don't think it will fade away, especially given the climate situation and in general, the environmental situation.
I agree, and to Kirsten's point, the wildfire scenario in a number of countries is a really important topic and issue, and understanding how we manage that risk and monitor sort of where fire breaks are and how that sort of fuel source is looking and changing is quite an important risk mitigate.
Especially here in Austria, because we live in forest cities.
Yes, yes.
According to a certain someone.
Yes.
Very well. Yeah. Thanks a lot to you, Kerstin. Thanks a lot to you, Matt. It was a pleasure to having you.
Thank you very much. Appreciate it.
We definitely stay in touch, and I hope you still can enjoy some productive meetings afterwards. So see you
I have
soon.
a full day ahead. Yes.
Have a nice day in the future.
Thank you very much. Thank you.
Bye-bye.
Thank you. Have a great evening.